Okay, so we're diving into some seriously mind-bending stuff today. The 2022 Nobel Prize in Physics.
This one's a real head-scratcher, even for those of us who spend our days thinking about this stuff.
Right, this whole entangled photons thing.
Hmm.
So, to get us started, we've got the Nobel Prize press release, the acceptance speech, and the official scientific background, which, let me tell you, is pretty heavy reading.
Yeah, but it's fascinating stuff.
Absolutely. So let's break it down. For our listeners who might not have a PhD in quantum physics, what did these Nobel winners actually do?
Well, in a nutshell, they proved that this thing called entanglement, this almost unbelievable connection between particles, is real.
Okay, back up for a second. Entanglement. We're talking about two particles, maybe even light years apart, and what happens to one instantly affects the other.
You got it. It's like they're communicating faster than the speed of light, which, by the way, completely baffled Einstein.
Yeah, he called it spooky action at a distance, right? Did these physicists actually prove that this spooky action is real?
They did. It all started with a physicist named John Clauser. He designed this ingenious experiment to test something called Bell's inequality.
Bell's inequality. That sounds intimidating.
It's really not as complicated as it sounds. Basically, Bell's inequality sets a kind of limit on how correlated two particles can be if they're just behaving randomly.
Okay, so if the particles are more correlated than that limit allows, it means something else is going on, something like entanglement.
Exactly. And that's precisely what Clauser found. His experiment showed that entangled photons, those tiny particles of light, were way more correlated than they should be if they were just independent entities.
So they were breaking the rules.
In a way, yes. They were defying the limits set by classical physics, suggesting that there's this deeper connection, this entanglement linking them together.
Wow. But Clauser's experiment was just the beginning, right?
Right, enter Alain Aspect. He took Clauser's experiment and made it even more airtight, closing loopholes and ensuring there were no hidden signals messing things up.
So he basically confirmed what Clauser found, but with even more certainty.
Exactly. His work further solidified the reality of entanglement, pushing it from the realm of speculation into the realm of accepted scientific fact.
Okay, so we've got entanglement, it's been proven, but what can we do with it? What's the big deal?
Well, that's where our third Nobel laureate, Anton Zeilinger, comes in.
Hit me with it.
He's the one who took entanglement from a theoretical head-scratcher and turned it into a practical tool. One of his biggest breakthroughs was demonstrating something called quantum teleportation.
Hold on, teleportation. Are we talking beam me up, Scotty kind of stuff?
Not quite beaming objects from one place to another. Think more along the lines of information. Imagine being able to instantly transfer the exact state of one particle to another, even if they're miles apart.
Okay, that's still pretty mind-blowing. But how could we actually use this quantum teleportation? Give me an example.
Imagine a world where communication is completely secure. Instead of sending data as bits, which can be intercepted and read, you're sending it via entangled particles.
So you're saying we could use entanglement to create a completely unhackable communication network?
Exactly. Because if someone tries to eavesdrop, the act of measuring those particles, it changes them.
Wait, so just by trying to listen in, they'd be messing things up?
Exactly.
Yeah.
Both the sender and the receiver would know instantly that someone was trying to snoop because the entangled particles would be altered.
That's incredible. It's like a self-destructing message. No more worrying about hackers stealing your credit card info.
Precisely. And it's not just limited to communication. This technology has the potential to revolutionize fields far beyond that.
Like what? Give me another example. How else could we use this entanglement thing?
Okay, imagine being able to simulate complex molecules with perfect accuracy.
Okay, I'm following. But how would we actually do that with entanglement?
Well, it all comes down to the fact that entangled particles are linked in this really deep way, right? They share the same fate, so to speak. So if we can create entangled particles that represent the different atoms in a molecule, we can essentially simulate how those atoms will behave and interact with each other.
And by simulate, you mean we could use this to design new drugs or new materials without having to actually create them in the lab first.
Exactly. We could test out countless variations of a molecule in the quantum realm to see which ones have the properties we're looking for.
So it's like having a virtual laboratory where we can experiment with the building blocks of the universe.
Precisely. And the possibilities are pretty much endless. We could design drugs tailored to an individual's genetic makeup or develop new materials with unheard of properties.
This is starting to sound less like science and more like science fiction.
I know, right? And it all goes back to this fundamental property of the universe, this entanglement that Einstein himself found so puzzling.
Yeah, we've come a long way from spooky action at a distance. But before we get too far ahead of ourselves, can we rewind for a second?
Sure. What do you want to go back to?
I think I need a little more clarification on this whole Bell's inequality thing. It's like the key to understanding how we know entanglement is real, right? But I'm still a little fuzzy on the details.
Of course. It's a lot to wrap your head around. Let me try explaining it this way.
So it sounds like we've got this incredibly powerful tool, this entanglement, that could revolutionize everything from communication to medicine. But what's holding us back? What are the challenges in turning this quantum dream into a reality?
Well, one of the biggest hurdles is figuring out how to scale this whole thing up.
Scale it up. What do you mean?
Well, we've seen some amazing things with entangled particles in the lab, right? Small-scale experiments. But building large, stable quantum systems that can operate in the real world, that's a whole other ballgame. It's like we figured out how to build a high-performance race car, but now we need to make it street legal and reliable enough for a daily commute.
Okay, I like that analogy. But what makes it so difficult to build these large-scale quantum systems? Is it just a matter of making the technology bigger, or are there other challenges?
It's a lot more complicated than just making things bigger. Remember how we talked about entanglement being incredibly fragile, like a soap bubble that could pop at the slightest touch?
Yeah, that definitely stuck with me.
Well, imagine trying to maintain the entanglement of thousands or even millions of qubits while also protecting them from the slightest vibration, temperature change, or stray electromagnetic field. It's a monumental task.
So it's not just about understanding the theory of entanglement, but also about mastering the art of controlling these incredibly delicate quantum states in a very imperfect world.
Exactly. It's a huge engineering challenge. Researchers are exploring a bunch of different approaches to try to overcome these challenges.
Like what? What are some of the approaches they're taking?
Well, some researchers are focusing on developing new types of qubits that are inherently more stable and less susceptible to noise. Others are working on error correction techniques.
Error correction. So like quantum software that can compensate for the inevitable errors that pop up in these delicate systems.
Exactly. It's like having a super sophisticated spell checker for your quantum computer, constantly correcting those tiny mistakes before they can cause a major problem. And it's not just about making the technology more robust, it's also about closing those loopholes we discussed earlier.
Right, the ones that Aspect and Zeilinger worked so hard to close. Were those loopholes just theoretical issues, or did they also reflect these real-world challenges of building robust quantum technologies?
They were very real vulnerabilities that could undermine the reliability and security of these technologies. Closing those loopholes was essential for paving the way for the quantum revolution we're talking about.
So their work, while incredibly complex, was essential in moving us from a world of what if to a world of how do we actually build this?
Exactly. And as we venture further into this uncharted territory even more, questions and challenges are bound to arise.
Like what? What kind of questions?
Well, for instance, as we develop more powerful quantum computers, how do we ensure they're used responsibly?
That's a great question. It's one thing to talk about all the amazing things we can do with this technology, but what about the potential downsides? Could this technology be used for harmful purposes?
Absolutely. It's crucial that we have open and honest conversations about the ethical implications of quantum technology. As we develop these powerful tools, we need to be mindful of how they might be used and what safeguards we need to put in place to prevent misuse.
It sounds like this quantum revolution, while incredibly exciting, also comes with a huge responsibility.
It does. But I'm optimistic. I think if we can approach this technology with a sense of shared responsibility, we can usher in an era of unprecedented progress.
Well, that's a hopeful thought to end on. We started with a Nobel Prize announcement and ended up on the very frontier of human knowledge, grappling with some of the biggest questions facing our species. It's been an incredible journey. Thank you so much for joining me today and sharing your expertise with us.
It's been my pleasure.
And to our listeners, thank you for joining us on this deep dive into the captivating world of entanglement. We'll be back next time with another mind-expanding topic, so stay tuned.